There's a gap between recognizing a concept and retrieving it under pressure, and the exam lives inside that gap. You've seen supervised learning, recall, Textract, foundation models, but seeing them on a slide is not the same as pulling the right one out of your head when 4 options are staring back at you, and 2 of them look correct. Stack Lessons, Episode 6. Here we go! By the end of this checkpoint, you'll have run 5 exam-style scenarios from the fundamentals block and walked the exact elimination logic that lands each answer. This isn't new teaching. It's a stress test on everything from the last 4 episodes to prove those ideas are retrievable, not just familiar. Here's the ground we've covered. In episode 2, we drew the nesting hierarchy, artificial intelligence wrapping machine learning, wrapping deep learning, wrapping generative AI. Episode 3 split the 3 ways a machine learns: supervised, unsupervised, and reinforcement. Episode 4 walked the lifecycle and the metrics that judge a model. And episode 5 mapped the managed AI services, the language and vision family. Today, we put all of it under pressure. Every scenario runs the same 5 beats. First, you read the situation and take it in. Then you pause and actually commit to an answer, out loud or in your head, before I say anything. Next, we hunt for the qualifier, the one phrase that quietly decides the whole question. From there, we eliminate the wrong options one at a time. And finally, we land the answer and name the rule behind it. That pause step matters most, so don't skip it. All 5 scenarios come from the fundamentals of AI and ML domain, and each one is a decision you'll make repeatedly on the exam. First, classification versus clustering. Second, precision versus recall. Third, Textract against 3 services that look like they'd fit but don't. Fourth, a traditional model versus a foundation model. And fifth, batch versus real-time inference. 5 decisions, 5 qualifier words to catch. Let's start. Scenario 1. Beacon Labs holds 40,000 patient records, and not one of them carries a label. The team wants to find natural groupings of patients with similar risk profiles, cohorts that will shape how the next trial gets stratified. So which learning paradigm fits? Supervised classification, supervised regression, reinforcement learning, or unsupervised clustering? Pause here and commit to an answer before we reason through it. The whole question turns on one gate, the same gate we built back in episode 3. Do the training records already carry correct answers attached to them? Here they don't. 40,000 records, no labels, and nobody has defined what the group should even be. That single fact closes the door on every supervised option before you read another word. Now, eliminate. Supervised classification needs predefined labeled categories, and we have none, so it's out. Supervised regression needs labeled continuous outcomes to predict, also missing, out. Reinforcement learning needs an agent earning a reward signal from an environment, and there's no environment here at all, out. What's left is unsupervised clustering. The groups emerge from the data itself, exactly like the k-means cohorts Beacon Labs found before. No answer key required, because the cohorts were never known in advance. Watch the word group, because it lives in both worlds. Discover unknown groupings that nobody defined. That's clustering. But sort each item into known categories using labeled examples. That's classification. Don't let the word alone decide for you. Ask whether the groups were defined in advance, and let that pick the paradigm. Scenario 2. A drug safety model flags patient records that may contain a rare but serious adverse drug reaction. Miss a real case, and it goes unreported to regulators, which is an irreversible, high-cost mistake. Raise a false alarm, and an analyst simply reviews one extra record, a minor recoverable cost. So which evaluation metric should the team prioritize? Pause and pick before I walk it. Amazon Web Services documentation puts the two metrics crisply. Precision evaluates how well the model avoids false positives, the false alarms. Recall assesses how well the model catches all the positive cases, the real ones. So each metric guards against a different kind of error. Precision guards against crying wolf. Recall guards against letting a real wolf through. The scenario tells you which error hurts more. Follow the expensive error. A missed real adverse event is a false negative. A genuine positive the model failed to catch. And in this scenario, that's the mistake you can't take back. To drive false negatives down, you maximize recall. This is the same logic Beacon Labs used on their adverse event flagger, accepting lower precision so almost no real case slips through. So precision is out. It fights false alarms, and here false alarms are cheap and recoverable. Optimizing for it would actually let real cases slip through, which is the one outcome we can't afford. Recall wins. It catches the highest fraction of genuine positives and accepts more false alarms as a fair trade. And notice F1 would only be the answer if both error types carried roughly equal cost. They don't here, so recall stands alone. Here's where candidates trip. The scenario says rare and serious, and the reflex is to reach for precision. But rare doesn't pick the metric at all. The direction of the expensive error does. When the costly mistake is missing a real positive, you want recall, no matter how rare that positive is. Read for cost direction, not for the word rare. Scenario 3. A lender receives thousands of scanned loan applications as PDF files. The engineering team needs to extract the borrower's name, income, and loan amount, and that data lives in structured form fields printed on the scanned pages. Which Amazon Web Services service fits? Amazon Textract, Comprehend, Recognition, or Kendra? Pause and pick. Picture these four as a document team, each with one job. Textract is the scanner operator, digitizing physical files and pulling out the text and form fields. Comprehend is the text analyst, finding meaning in text that's already been extracted. Recognition is the photographer, analyzing objects, faces, and scenes inside images. And Kendra is the reference librarian, searching across an entire corpus to answer a plain English question. Assign the role the scenario actually needs, and the service picks itself. The official definition nails it. Amazon Textract detects and extracts printed text, handwriting, structured data like fields and their values, and tables from images and scans of documents. That's this scenario word for word, structured form fields pulled off scanned pages. There's even an analyze lending capability built for exactly this. Mortgage and loan document packages. So the elimination fits in one line. Pull data out of a scanned file, that's Textract. Comprehend needs text that's already extracted, so it can't be the reader here. Recognition analyzes visual content, not dense document forms. And Kendra searches across a library you've already digitized. It doesn't do the digitizing. The need is extraction, so Textract lands. Scenario 4. A law firm needs to classify every incoming contract as an NDA, an MSA, or an SOW. They already have thousands of past contracts labeled by paralegals. But General Counsel adds one hard requirement. Every classification decision must be auditable, feature by feature, so they can show which contract attributes drove it. Traditional supervised model or a generative foundation model? Pause and pick. The exam guide names the deciding factors directly: regulatory concerns, explainability requirements, and operational constraints. When a scenario hands you one of those phrases, it's telling you which model family to reach for. Here, General Counsel wants an audit trail. That single phrase is the whole answer. So here's the pause and predict moment. Which one wins? The more powerful model or the more transparent one? It's the transparent one, and here's why. A foundation model produces probabilistic, opaque outputs. It can't give you a clean feature-by-feature audit trail, so it's the wrong fit for a regulator. A traditional supervised model, a logistic regression, or a decision tree makes every decision traceable to specific features. And the labeled contracts to train it already exist. Explainability forces the choice. Bank this signal word for the exam. When you see regulatory concern, explainability requirement, or a demand to justify each decision, the arrow points to traditional machine learning, not a foundation model. Foundation models bring flexibility and scale, but interpretability is where the older, task-specific models still win, and the exam knows it. Scenario 5, the last one. A bank needs to generate a credit risk score for every one of its 2 million active accounts. Risk analysts pick up those scores the following morning, and no real-time response is required at any point in the flow. Batch inference or a real-time endpoint? Pause and pick before we read the cues. Read the 3 cues the scenario dropped in. Volume first, 2 million accounts scored in one go, a huge data set. Schedule second. It runs once and results are needed by morning, a periodic job. And latency third, no immediate response is needed anywhere. When those 3 cues all line up, large volume, on a schedule, with no latency demand, they point straight at batch inference. This is the catering company from episode 3, not the barista. So why rule out the real-time endpoint? Because a real-time endpoint is always on infrastructure that bills continuously, whether requests arrive or not. Paying for that around the clock to serve one overnight bulk run is pure waste. Batch transform spin-up processes the whole dataset from storage, writes the results back, and shuts the compute down. For a periodic, latency-tolerant job, batch is both the correct and the cheaper answer. Let's compress all 5 into shortcuts you can fire in seconds. Do labels exist? No labels means clustering. Which error costs more? A missed positive means recall. Do you need to pull data out of a scanned file? That's Textract. Is explainability required? Reach for traditional machine learning. And is it high volume, on a schedule, with no latency demand? That's batch inference. 5 signals, 5 answers. Before we move on, one honest bit of homework. Notice which scenario made you hesitate, because that hesitation is the exact spot to go back and deepen. If you remember nothing else, remember this. Every fundamentals question turns on a single qualifier phrase, so find that phrase before you even look at the options. And the exam scores overall with no per domain minimum, so reason carefully rather than rushing. Now let's see how well you absorbed all of this with a quick 5-question quiz. All right, time to put your knowledge to the test. Question 1. A research team has 80,000 unlabeled customer records and wants to discover natural spending pattern groups that nobody has defined in advance. Which approach fits? Is it A, unsupervised clustering, B, supervised classification, C, supervised regression, or D, reinforcement learning? Lock in your answer before I give it away. The right call here is A, unsupervised clustering. There are no labels, and the groups were never defined ahead of time, so the structure has to emerge from the data itself. Classification and regression both need labeled training data, and reinforcement learning needs a reward signal from an environment. None of those apply. Question 2. A tumor detection model flags CT scans for radiologist review. Missing a real tumor is the most expensive, irreversible error, while an extra scan sent for review is only a minor cost. Which metric should the team optimize? A, precision. B, recall. C, accuracy, or D, mean squared error? Think about which error costs more before you answer. This one is B, recall. Missing a real tumor is a false negative, and that's the error you can't take back. Recall measures how many genuine positives the model actually catches, so maximizing it minimizes missed tumors. Precision fights false alarms, which are cheap here, and mean squared error is a regression metric that doesn't even apply to a classification task. Question 3. A healthcare company needs to extract structured field data from thousands of scanned insurance claim forms stored as PDF files in S3. Which service should they use? A. Amazon Comprehend. B. Amazon Recognition. C. Amazon Textract. Or D. Amazon Kendra. Pause here if you want more time. It has to be C. Amazon Textract, and here's why. The need is pulling text and form fields out of scanned documents, which is exactly what Textract does. Comprehend only analyze text that's already been extracted. Recognition handles images and visual scenes, and Kendra searches across a digitized corpus. Only Textract does the extraction itself. Question 4. A bank's compliance team must classify loan applications as approved or denied, and regulators require a written explanation of every decision, citing which applicant attributes were decisive. Which approach is most appropriate? A generative foundation model through Amazon Bedrock. B, a retrieval augmented generation pipeline over policy documents. C, a large language model prompted with each application. Or D, a traditional supervised model such as logistic regression or a decision tree. Run the decision rule from earlier before you answer. If you said D, well done. The deciding signal is the explainability requirement, and traditional supervised models give you a clean feature-by-feature audit trail. The other three all lean on foundation models or large language models, which produce opaque, probabilistic outputs that can't justify each individual decision to a regulator. Last one, question 5. A logistics company predicts delivery delays for 500,000 packages each evening, so customer service can proactively contact affected customers the next morning. There's no real-time latency requirement. Which inference mode fits? A persistent real-time endpoint. B, serverless inference with scale to 0. C, batch inference. Or D, asynchronous inference. Got your pick? Let's see. The answer is C, batch inference. High volume, a fixed evening schedule, and no latency requirement all line up, and that trio always points to batch. SageMaker Batch Transform processes the whole dataset at once and then shuts the compute down. A real-time endpoint would build continuously for no reason, and serverless and asynchronous modes are built for intermittent or large payload individual requests, not one big scheduled bulk run. That's the full picture on Checkpoint 1, AI and ML Fundamentals Retrieval Challenge. Subscribe if you want the rest of the Amazon Web Services AI Practitioner Prep delivered straight to you, no searching required. Drop a comment with the part that surprised you. That feedback genuinely steers the channel. Got an exam you want next? Say the word below. And if anything about the style or the speed would work better for you, let me know. See you in the next lesson.